So let's repeat a few points about the atmospheric circulation in terms of the cells again, with a slightly different way of getting at it from Chris Karnauskas, who has worked on the Hadley cell for a while, actually, even from the historical perspective of Haley's idea, Hadley, and then further ideas that emerged. So let's say we start with this, where we are looking at low pressure at the surface in the low latitudes because it's warm, high pressure at the surface at the poles because it's so damn cold, and that by the same token we know that in the upper atmosphere there is high pressure in the low latitudes and low pressure at high latitudes. So this will drive a pressure gradient at the upper level and a flow from the high pressure towards the low pressure, and there will be a return flow from the high pressure towards the low pressure at the surface or lower level of the atmosphere. If you remember, Hadley basically used this idea, and then he realized that because the atmosphere, the Earth is rotating faster here than here, he realized that the air that's coming here is going to fall behind, so turn eastward, and the air that's going here is going to move faster, so it's going to turn westward. So he created westerlies and easterlies. So he was basically right in that broad sense, but of course he made a mistake in assuming that there will be just one cell. So if we add the Coriolis in the way Hadley imagined, but more formally as we learned, then you know that the F times V is going to turn it to the right for the northward flow, and for the southward flow it's going to turn to the left, to the right. Oops, let me make sure I'm doing this right. Why am I always screwing this up? So as the air is coming south, it's going to turn towards the east, and as the air is going towards the north, it's going to turn towards the right. So we are basically going to end up with northeasterlies and westerlies and polar easterlies, and you have to add some additional dynamics to realize that the winds cannot go all the way from the low latitudes to high latitudes, so you end up with a descent or subsidence at some latitude, which depends on lots of details of how the scale is selected for the termination of this Hadley cell written as H. So you have this Hadley cell with equatorward flow here, rising motion here, poleward flow here, transporting some energy, and then this sinking air is diverging, so some flow is also going towards high latitudes, and polar air is coming to lower latitudes. They are meeting at the mid latitudes and creating a rising motion here, which showed us the rainfall second peak at these latitudes as well, and of course that flow diverges at the top as well, and you can see the Ferrel cell and the polar cell here. So typically these are called thermally direct cells because it's directly related to cold air sinking over cold temperatures and warm air rising over warm temperatures, but this is an indirect cell because you are actually having rising motion over colder air. So that's you can think of it as a kinematic gear that connects the two thermally direct cells. So this cell and this cell are connected by this gear in the middle. So to look at the vertical motions and to do zonal mean meridional cells more formally, we need this information. It's common practice in atmospheric science to use pressure P as a vertical coordinate rather than the Cartesian coordinate, Cartesian altitude Z. The details are such that it removes density from the equations, which is very inconvenient because density cannot be directly measured, and it cannot be ignored in the atmosphere because atmosphere is a very compressible fluid. So using the ideal gas law P equal to rho RT, we can actually replace density with pressure and temperature, which is what gives us this pressure coordinate. Pressure is dropping logarithmically in the vertical, and z is of course increasing, so we can use that relation to replace z with p. In that case, vertical velocity is defined as omega equal to dp dt rather than w equal to dz dt, and since dp dz is less than 0 in the atmosphere, pressure is high at the surface, decreases to the upper atmosphere. The definition of stream function emerges: v equal to deep psi dp and omega equal to minus deep psi dy. Few steps are jumped over here, but basically if you take the zonal mean meridional circulation like we did here, then the flow becomes non-divergent because the vertical meridional plane, the flow has to be non-divergent because you have assumed a zonal symmetry or axisymmetric flow around the rotational axis. So that allows you to define a stream function. Zonal mean meridional overturning stream function is computed by taking vertical or pressure integral of the zonal mean meridional velocity and applying an assumption that the atmosphere is non-divergent, i.e. the continuity equation is valid, and it looks just like the incompressible one we saw where we said du dx plus dv dy plus dw dz is 0. In this case it becomes dv dy plus d omega d p is 0. So instead of z will be p coordinate in the vertical. Okay, so knowledge of the velocity field, which is much less well observed, is not required to calculate the stream function. Another advantage of to the stream function approach of characterizing the overturning circulation in the atmosphere is that we don't need knowledge of the velocity field. Okay, so that's our definition: v equal to minus del psi del z, w equal to del psi del y. If you don't know the definitions of stream function, basically these are lines to which are defining the flow. Flow is always tangential to these streamlines, as you remember from your basic fluid flow. So here is the result. We are looking at climatological zonal mean meridional overturning stream function in kilogram per second based on observational data from NOVA-NCEP reanalysis. Reanalysis, as we have said before, is a merger of models and data to fill the gaps and produce continuous graded data. This is for the annual mean, this is for the boreal winter, and this is for the boreal summer, it should be, right? No, sorry, that's for the El Nino. Boreal winter El Nino anomaly. Okay, so this is climatology, this is for El Nino. So what do you expect in the annual mean? You have rising air showing stream functions in the middle. Obviously there is an asymmetry because the ITCZ is generally to the north of the equator even when you make a zonal mean. So you have a Hadley cell showing up here and a Hadley cell showing up here, and the polar cells are barely seen and the Ferrel cell is not seen so clearly in this case when we do the zonal mean meridional section. And for the boreal winter you expect that the sun is to the south and ITCZ is towards the south, so it moves with the sun, goes northward during boreal summer, migrates southward during boreal winter, which means the strongest rising motion is in the winter hemisphere. So you can see you can see the clear cross-equatorial flow here feeding the Hadley cell, and the boreal winter has a weaker Hadley cell here and a stronger Hadley cell in the annual mean here. During El Nino we will see that the whole system gets shifted. The West Pacific shifts, the convection moves from the West Pacific maritime continent towards Central Eastern Pacific, which changes the structure of the ITCZ and the Hadley cell and so on. So you can see here that the if you put the reference, the contour of the middle panel here, this one, you can see how the entire system is shifted during the boreal winter of an El Nino year. So the Hadley cell seems much weaker, and the Ferrel cell here looks much stronger. There is a shift of the entire flow system, and the southern hemisphere looks very different as well. We'll come to that a little bit later on, but just keep that in mind. Okay, so we will come back and look at the energy transport and other things in the next podcast. But we are repeating some of the points, but with a slightly different bent. It doesn't matter. We are soon going to translate this into atmospheric response to ocean forcing to understand how ocean affects climate and climate change as we go forward. Okay.